So my name is Raul Muñoz. I am the head of the Packet Optical Networks and Services Research Unit at CTTC in Barcelona, in Spain. And I'm going to provide you an overview on some specific activities that we are developing in the FLEXI-SCALE project that are mainly related with the sustainable control of packet and optical transport networks for 6G. So first of all, let me to briefly introduce you a little bit the FLEXI-SCALE project in order to have a better understanding on what we are doing in the project. So we are a project that was founded in the first call. So it means that we started in January 2023, and it is led by Professor Yanis Tonkos from the University of Patras. Let's say that we are quite large consortium. As you can see, it's composed by 15 partners, and not only from the European Union, but also from Switzerland and from Israel. So in FLEXI-SCALE, we are basically dealing with optical, mid-haul, and backhaul. So basically, what does it mean? Maybe you can use another pointer. Yes, here. So basically, as in the run, it can be decouple or decompose into remote unit, distributed unit, and centralized unit, defining the front-haul, mid-haul, and backhaul to reach the core network. And below, you can see the transport network that is required in order to provide services to these segments. So basically, FLEXI-SCALE is precisely working on the backhaul side. And partially, we are also supporting, touching somehow the mid-haul. So basically, we are providing transport services between the centralized unit and the core network, and also partially between the distributed unit and the centralized unit. The main innovation that we are carrying out in FLEXI-SCALE is, as I said before, on the transport network, but more in particular on, for example, on the transceiver side. So the transceivers is one of the elements that are key because they provide connectivity to the network. So basically, they allow the IP radars to provide connectivity to the optical network. And our goal basically is to increase the capacity up to 10 terabits per second. In addition to that, we are also targeting to increase the capacity of the network links by, let's say, making use of some new dimensions that have not been previously considered, of course, in the commercial side. The first one is the wideband. So basically, taking into account that in the fiber, there is, let's say, a portion of the spectrum that has been traditionally used for communications, but the spectrum available is much larger. What happens is not so optimal. So in this project, we are also extending the spectrum that is available in a fiber. It can be used for communication purposes. And we are also making use of the spatial dimension. That it means that, as you can see here, between each pair of node, instead of having a single fiber, you may have a bundle of fibers. So the final goal is to increase the network capacity up to 1 petabit per second. And of course, it means that also this node, this optical node, the switching capacity must also increase because we are basically offering more capacity overall. And of course, another innovation is the SDN automation of the complete packet optical and cross-haul network. So this is the multi-granular optical node that we are developing in FLEXI-SCALE, where, as I said before, we are combining many different technologies that were not, let's say, considered before. So in addition to the wavelength switching, that is the way that currently we have to provide connectivity services, we also deployed a new element that is the waveband selective switch, that basically what allows is to switch bands within a fiber. And we can also switch fibers in such a way that we are stacking, let's say, several switching layers at the wavelength level, at the waveband level, and also at the SDM level. This is the reference network architecture that has been defined in FLEXI-SCALE. So basically, as you can see, it is composed by rings in the access network that are providing connectivity to the base stations and that are making use of an access radar. And they are connected to the access central office, where we can find the first aggregation router. And then several access central office that are also connected using a ring topology are connected to a regional central office that are also connected to a regional core. And then finally, we have many different regional central offices that are connected, all them together, following, in this case, a mesh topology. As we have said before, one of the main novelties is that we are using multiple fibers in parallel, and we are also using multiple bands within a fiber. So it increases considerably the complexity of the node because we need to switch at the IP layer, but we also need to switch at the wavelength, waveband, and fiber level. So this is, let's say the overall transport network and control scenario that we are considering in FLEXI-SCALE. As you can see at the bottom, we have this multi-granular optical network that is controlled by a dedicated optical listening controller. Then on top, we have the IP layer. This is a hierarchical one, of course, composed by IP radars in the access segments and that goes through the core network. And in this case, we have a packet SDN controller that is responsible for the control of this IP layer. All them are, let's say, under the umbrella of this end-to-end transport SDN orchestrator. And then on top, you can see, because Scale is not dealing at all with RAN or core network, but for illustrative purposes, in order to clarify how the transport networks are integrated in the overall end-to-end management system, you can see that we have here the remote unit, distributed unit, and centralized unit, all them, let's say, managed by a RAN controller. In a similar way, we also have the core network controller for the core network functions. And then we have this 6G management end-to-end system that interfaces with the RAN controller, with the core controller, but also with the end-to-end transport orchestrator that is the one responsible for providing transport connectivity services across the IP layer and this new multi-granular optical node. So this is an example on how we are, let's say, targeting the management of these multi-layer packet optical networks. Something that I have also mentioned at the beginning of the talk is that we are also targeting this energy efficiency management. So it is, let's say, an activity that is addressed different ways in FLEXI-SCALE. Now, of course, I'm going to focus at the networking level, but also at the device level design of the nodes, of the transponders. So energy efficiency is something that is a must. So it's one of the main design principles. But in our case, basically the traditional way that this kind of network works is that when you want to provision, first of all, you have IP radars, as you can see here. Whenever you see a link between an IP radar, in fact, it is a logical link. So it means that below you have an optical channel, a physical optical channel that is providing connectivity between the IP radars. And then whenever you want to have a flow connectivity service between a pair of source and destination radars, between the access and the core, you have I hope IP routing, as you can see here in this picture. So one of the objectives that we are targeting in FLEXI-SCALE in order to reduce the energy consumption is precisely to remove those IP radars that are strictly not necessary. So basically by passing the IP layer to the optical layer. So basically what does it mean? It means that, for example, we want to also have the same service that we have seen before, but in this case, between this IP radar and between this IP radar, we can dynamically provision an optical channel. This optical channel is represented as an IP logical link in the IP layer. So now they have a direct link. And then, of course, we can start the retransmission of the IP flow. So this is the functional architecture that we are developing in FLEXI-SCALE. First of all, you can see here the two main optical devices that have been developed. On the one hand, we have this Ultra-Wideband and SDN optical node. So this multi-granular optical node that I have mentioned before. We also have the transceivers. And what we have done is to, I've also said before, develop a dedicated optical listening controller that is in charge of configuration of both elements, and also a monitoring and telemetry manager and a data analytics manager that is in charge of collecting information from both devices and also processing that. On top, we have a sustainable transport SDN orchestrator that, together with the energy efficiency multi-layer traffic agreement algorithms that are also designed in the project, we can perform this energy efficiency management at the flow level. And this SDN orchestrator also interfaces with a packet SDN controller. And here you can see this hierarchy at the IP level that I have mentioned before. And of course, our goal is to also provide the normal interface of this transport orchestrator, so of the transport or the cross-haul orchestrator towards the end-to-end management system in order to be integrated to a RAN controller and to the core network controller. Just to show you the complexity that this kind of networks requires, because now complexity, of course, in terms of provisioning the service, a connectivity service, because now we are required, let's say, to extend, as we have said before, the wavelength switching, that is the traditional way of offering connectivity services in the optical domain, to also waveband switching. So this large spectrum that I have mentioned before, in order to make use of the C and L bands in addition to the S and L band in addition to the C band, and also spatial switching. So the SDM dimension where we can also directly switch fibers. So that means that whenever we want to deploy the service between a pair of IP routers, we need to provision a spatial channel in the spatial domain. It belongs a virtual link in the waveband domain. Then we provision a waveband channel, and then it becomes a virtual link in the WDM domain. And then we also deployed an optical channel between a pair of optical transponders, and it belongs a digital link. And finally, we can deploy a digital service between a pair of IP routers, and it is represented as a virtual packet link. So just to show you the hierarchy that we need to manage and the complexity of this kind of network. So the approach that we are following in FLEXI-SCALE to develop this control and orchestration system that I have just presented is to rely on the Teraflow SDN controller. First of all, what is Teraflow? Teraflow is an open source SDN controller that is developed within the ETSI open source group, and that is based on the cloud-native architecture. There's no need at all to explain what is cloud-native architecture, since it has been mentioned many times today. But as you can see here, we, let's say, develop many specific microservices, each of them dedicated to some specific functionalities that are required for an SDN controller. So this is the release 2. By the way, soon we're going to release also the release number 3. So with new features that, of course, will be also that will also include part of the activities that we are doing in FLEXI-SCALE. But as you can see here, one of the main issues is that, of course, we need to extend the release, because unfortunately, these features that I have mentioned before, not all of them are, let's say, properly addressed by the current implementation of the Teraflow. In particular, I'm referring to the multi-layer support of packet and optical, also the energy efficiency monitoring and telemetry. It's very important. Also the automation loop, and that means the data collection, but also the analytics in order to identify some insights, and also the decision part. So what should I reconfigure on my network? And the last feature that we are also extended in Teraflow is precisely this support on multi-granular optical nodes based on wavelength, waveband, and fiber that I have mentioned before. So the idea is that Teraflow is a flexible framework based on microservices, as I mentioned before, and therefore we can instantiate that in a way that it can act as the end-to-end transport orchestrator, but also at the same time, another instantiation can act as the optical SDN controller, and another instantiation can act as the IP SDN controller, in such a way that all the different elements that are required in the overall end-to-end orchestration system, we can manage that by properly instantiating short Teraflow system. One of the key elements that now we are, let's say, developing is precisely the closed loop that is required in order to introduce automation. So network automation, as you have seen, it's required to manage the energy management, but also, let's say, because we are also developing some other use cases. And the main idea behind that, I'm not going to the details because are very specific on the Teraflow architecture, but basically the main detail is that we can support, let's say, the collection of data through through the different interfaces. We can also perform analytics of this data by properly defining some specific KPIs that need to be validated. The outcome of these analytics are precisely insights that based on the specific policies that has been defined, when we request a service, we can also trigger the reconfiguration of the specific service. So this is the overall closed loop, and these are the different microservices that are going to be developed. In fact, are being developed right now. So energy efficiency management. it's very important for us. What they have said before is to keep track on what is the energy consumption, because based on that we can optimize our network. So this is the architecture that we are developing in FLEXI-SCALE. So at the bottom you have the infrastructure. In the infrastructure, basically what you have are the IP layer, the optical layer, but also in addition to that we also consider computing layer, because basically computing resources are going to be distributed everywhere in order to deploy the specific applications that are needed. And the idea is that on top, we can, let's say, deploy a streaming layer that is responsible for the event notification and subscription. And then on top, we have the option of storing, let's say, all the information that is provided by the streaming layer, but also we can perform analytics directly in such a way that the outcome of these analytics can go to the decision engine and the execution engine. But it is that we can work both with monitoring, but also with telemetry. So this is the specific architecture that has been also developed. You can see more or less some of the elements, the key elements that I have mentioned before. So here there is the Kafka bus that allows basically this event notification and subscription. We also have Prometheus in order to collect and store all the information. Also all the analytics backend that in this case is based on a Spark, in such a way that we may have analytics that could directly interface with, let's say, with Kafka bus or through Prometheus, if let's say they are not based on critical applications. Then this is some example, let's say, just to show you basically preliminary results on this platform that is used for collecting energy consumption. So this is at the bottom you have the topology, let's say, that we have used. This topology includes data center, so the edge and the core, also includes IP layers, so the two IP radars, and also include ROADM, so the optical layer. And here we have some monitoring results for the data center, for the IP radars, and also for the ROADMs. And the idea was to, let's say, switch on a new interface from, well, in fact, from 10 gigabits per second to 100 gigabits per second, just to see what was the power consumption, and also to instantiate new services. And we have used, let's say, both, on the one hand, the API that the system itself provides, but also sensors in such a way that we can verify that what the vendor provides corresponds to the actual consumption that is measured by deploying a sensor. And it's quite funny because in some cases we can see that there are some difference, but in general, let's say all them follows the same trend. And definitely when you switch on any kind of interface, it consumes more power. So with that information, what is our purpose? To perform autonomous energy efficiency management. So what does it mean? Let's consider this network. So as you can see here at the IP layer, we have multiple IP flows that have been deployed. So one of the scenarios that we may consider is precisely the reconfiguration of those IP flows, especially, let's say, in those time, in those time areas where there are not too much traffic. But the idea is to reconfigure these IP flows in such a way that we can free up some specific links. And it will allow, of course, to remove these virtual links by also removing the associated optical channels, and also, of course, switching off the IP interfaces or the IP or the pluggables, let's say, the ports, the IP ports. That is precisely one of the elements that introduce more power consumption. But it doesn't come for free, because here, as you can see, there are also some other intermediate IP radars that we are increasing the traffic flows, and therefore will also increase more traffic. So that's why these tools that are continuously monitoring the consumption at different layers is a must. So that's all on my side. In case, of course, that you have any question, I would be very happy to answer that.
The one is, how can you guarantee the continuity of sub-wavelength along path of multi-hops?
Sub-wavelength, it's not clear to me what does it mean, continuity of the sub-wavelength. So I understand that because at the sub-wavelength level, at least in our case, we are considering, let's say, this waveband, but also fiber switching. So in some cases, there is need to have continuity, in particular for waveband, because the conversion from one band to another band, definitely it's something that there are some specific devices in Japan that are working with that approach, but let's say that we are there is no interest basically on going that direction. So that's why you need to keep this continuity at the wideband level, definitely, and it is performed by, let's say, on the algorithm side. So by algorithm, when you compute your path, you can satisfy this continuity. And at the fiber level, in this case, there is no need to guarantee this continuity as long as you are basically working with a bundle of fibers, because there is no crosstalk, between fibers. And in case that you are using a multi-core fiber, where within a single fiber you have multiple cores and all of them are together, then of course you will need to have some kind of continuity just to avoid, let's say, to have too much crosstalk in one of the cores. However, the current designs of the fibers basically reduce a lot the crosstalk between cores. So it's something that in practice will not be required to have this continuity. I don't know if it was a question, but anyway, I try to basically to provide an answer for the different levels.
Thank you. And there's another question in chat we can take. The configuration of the flows is done on different domains with different timescales. How do you address this?
Yeah, definitely. So the configuration of the flows is performed on different domains, as we have shown. It's clear. In fact, in the point of domains here, it's not clear to me if they are referring to administrative domain or technological domain, but definitely technological domains, yes. We have shown that. So we have multiple technological domains. So the idea is that we need to orchestrate all them together. And that's the main reason why on top we have this end-to-end orchestrator, transport orchestrator, because it is required to interface with all the technological domains. If the question was more on the administrative domains, in such a way that we can segment our network, let's say, into multiple administrative domains, then of course the architecture should be, let's say, improved in order to also consider that dimension. That is something that in FLEXI-SCALE we are not doing. I think that exactly, yes, there is another question. Well, it's the same question. Exactly the difference in time scales, how this will be addressed. Yeah, so the time scales, it's something that our, let's say, design is that who defines the, let's say, the time scale are the services at the IP layer. So the IP layer basically is the one that is defining when we want to have any kind of connectivity services. And then it triggers, let's say, dynamically the connectivity services in the underlying layers in such a way that from that perspective, let's say, there are no difference in time scaling. But of course, it's clear that we are always considering circuit switch. So that means that the optical layer needs more time to be reconfigured or provisioned, let's say, than the packet layer. But here we are not competing. Let's say the optical technology is not providing any kind of packet-based solution. It's providing a connectivity service between IP layer. So it can, let's say, there could be a difference in time scales, but it doesn't have any impact at all.
Are you factoring in multi-tenancy, multi-MNO fronthaul at the HL5 and cell-site router wireline convergence?
Well, wireline convergence. Let's say that it's a very good question, but it's not addressed at all in FLEXI-SCALE. Because we have, what I have mentioned, the scope of FLEXI-SCALE is mainly on the backhaul, and partially we also address mid-haul, but very limited. So this part that is more related with HL5, so the access rather in the cell sites, and also what kind of technologies could be used for fronthaul, or let's say, or for the fixed access that are giving services to the cell sites. It's something, let's say, that in this project, in FLEXI-SCALE, we are not properly addressing. So I cannot, let's say, give you an answer on behalf of FLEXI-SCALE.
Thank you. General question, how will Hexa-X-II be different in 2024 than 2023? Any new directions? So I think Hexa-X-II will continue working. The first year was a lot of scoping and looking at the problem statements, whereas 2024 will look more at more details on the solutions and more on evaluations.
If I may, Patrick, continue with that. Also, one central thing with Hexa-X-II is this 6G system blueprint and bringing the things together. And concerning this one, we will release around every half a year a new document. And so this continues also during this year. And along the lines that Patrick was already saying, so also along those lines, in all the technical areas, we are moving forward with approaching new deliverables.
Another question here. Is Teraflow capable of managing radio resources?
No, definitely not. Teraflow is a transport SDN controller. It, let's say, provides services to any kind of transport technology. And that means, as I have shown, the IP layer, the optical layer considering this multi-granular approach, but definitely not on the radio side. There is some specific implementation of Teraflow that were using microwave links, but were used for transport purposes. So were basically used for providing connectivity between base stations. But again, on the transport side, Teraflow, by definition, is a transport SDN controller, and basically has nothing to do with the RAN, so with the radio resources.
Okay, thank you. Doesn't seem to be any further questions. So then I would like to say thank you to all the speakers, both yesterday and today, and thanks to the entire audience. From Hexa-X-II, we really appreciate the great effort all the speakers have given and the great attention that the audience provides. So I don't know if Mikko wants to say some final words.
Yeah, I would like to support what you already said. Thank you very much to all the speakers and the audience for very active participation.